Hello, everyone. I'm going to be talking about intermittent turbulence in many body systems. I'm Guga Gogia, and this is my presentation here. Intermittency is a common characteristic of complex systems that are made out of many interacting elements. Dynamics of such complex systems is frequently dominated by big jumps as a measure of intermittency. For example, sudden outbreak of diseases, ice ages, network-wide blackouts, or financial markets crashing. Probably the most famous example of intermittent dynamics in physics is transitional turbulence. Reynolds, even in his original experiments, observed that while he was pushing the fluid through a pipe and inserting dye to study the behavior of the fluid, he noticed that between laminar and turbulent states, the transition was not sharp. Actually, the transition was dominated by this transitional regime where intermittently puffs of turbulence would be generated that would travel down the pipe and collapse back into laminar state. He tried to characterize the fluid flow with famous Reynolds number that represents ratio between inertial and viscous terms. However, there was no critical Reynolds number value above which the fluid flow would have been turbulent and below which it would have been laminar. The reason for this is that laminar pipe flow is linearly stable for all velocities. For turbulence to develop in such regimes, you need very fast flow and strong perturbations. And there's two general ideas of driving and structural heterogeneities, and their interplay between them is going to be the core of this presentation. There are some other examples of intermittent bursting in fluid. This is from a paper that is under review currently from Andrei Pototsky's lab. And you can notice that this liquid immersed in oil droplet immersed in water that is vibrated at 60 hertz frequency experiences this intermittent generation and bursting of Faraday waves, one of which you just saw. However, what I'm going to be talking to you today about is not about liquids, at least not in conventional terms. It's about a crystalline structure that experiences intermittent switching between gas-like and crystalline states. And this will be very similar conceptually to transitional turbulence. Here's the video of the phenomenon. You will notice two things. One of them is blinking of the whole layer, which means that the particles are moving in and out of the laser sheet that's illuminating them from the side. And then the whole sample is rotating, which is due to Earth magnetic field in Elena that's rotating the ions in the chamber and dragging the particles along. And you can see that it just like recrystallized, and now the blinking gets really synchronized, and this blinking builds up. You can start noticing that some of the holes that are due to heavier particles in the center of the sample, you will see particles showing up in those holes. And there's this nucleation event that melts the system into a gas-like phase. So described as individual particles having a lot of energy in the plane that we are observing them in. And then it all comes back to a crystalline state again. So to give you an idea what you were just looking at, this is all happening in this vacuum chamber where we ignite argon gas into plasma using this electrode that we apply radio frequency voltage to, and everything gets charged negatively, including the particles that we add through mechanical shaking and the electrode. And there's going to be repulsion between the particles and the electrode. That's why the particles are levitating. And what I just mentioned about the characterizing the melted and crystalline states, this can be done using a kinetic energy in XY plane. XY plane being the plane that we were looking at. You can notice that like crystalline states, which are associated with lower values of kinetic energy in XY plane, their duration changes from one event to another. And this crystalline state is punctuated with this very aggressive and sudden transition to gas-like phase, in which the system spends some time and then slowly and gradually relaxes. So we started using numerical simulations with minimal ingredients to understand the core of the problem. We started with very simple system where particles are confined by harmonic vertical and horizontal potentials and are interacting with each other with shielded Yukawa, shielded Coulomb potential. And we had two forces, Langevin forcing in Z direction to simulate the vertical oscillations and viscous damping due to gas. There's no plasma-specific properties in the simulations. And finally, but very importantly, we introduced disorder in the system which is simulated by Gaussian distribution of particle masses that have mean M and coefficient of variation CV. So CV describes the extent of disorder in the system. So you can see here video from simulation where we have a side view right here, top view, and then fractional kinetic energy in XY direction. You can notice that initially XY energy is very low. Most of energy is concentrated in this vertical oscillations. And then suddenly there's this melting event, which melts the system irreversibly, or not irreversibly, but quite reversibly, as a matter of fact. And it spent some time in this melted state. If it was exactly ideal gas, it would reach the values of 2/3. However, we are constantly forcing the system in Z direction, so it's impossible to reach the 2/3 value. And then gradually the system relaxes back into crystalline state, as manifested by the gradual decrease of fraction of kinetic energy in XY direction. And then it really recrystallizes. As you can see, there's not much energy in XY plane. And then there's going to be another melting event, which for the sake of time, I can skip, but you can find all of this information on my website. The way we characterize switching and the extent of intermittency is by looking at this delta XYs and taking Fourier transform of this time traces. What is really different between intermittent regime, which is for lower polydispersity, lower disorder of the system, and for higher polydispersity or higher disorder of the system is constantly turbulent, is that the intermittent one is going to have a lot more power under the low frequency modes of Fourier transform, meaning that there's more processes happening at longer time scale. So what we see here is by calculating switching intensity as the integral of Fourier amplitudes of the time traces of delta XY, we find that three distinct regimes. One is turbulent for higher values of CV and phi, which is the forcing. And then for intermediate values, there's the intermittent regime. And for very low values of both of those, we have laminar state. This also shows something that people have seen in fluid dynamics, where basically if you have very, very low CV, which would correspond to very smooth pipe walls, no matter what velocity you are pushing the fluid through, where here this is driving, the system will remain laminar. Same thing for very low driving and very large disorder. So finally, our simulations yield this dimensionless number that is very similar qualitatively to Reynolds number, where you have inertial term that parameterizes also the disorder or the wall roughness, and divided by gamma squared, which is viscous term. And for roughly unity of this value of theta, the switching is maximized, or the switching of the dynamics is mostly intermittent. And finally, we decided to describe our system energies in our system using interacting species, where A and B are two distinct species that are preying on each other. The way the equations worked out was that Newtonian mechanics kind of reproduced our conventional predator-prey dynamics. As power dissipated is equal to viscous force multiplied by velocity, which is gamma mv squared, and by saying that kinetic energy is roughly equal to potential energy, we can say that the sum of the two, which is mechanical energy, is equal to gamma mv squared. So this way, the death term, conventional death term in predator-prey systems is linear with both of the species numbers. And the second term, here we have predation, so-called, and here C is the disorder in the system, that the species only talk to each other if there's some disorder in the system. And there's this extra term from that differs or makes this equation different from the conventional predator-prey, which comes from scattering theory, that like the power transferred from A to B and B to A are not the same. And the difference between the two is this term right here. And finally, we have noise driving, which is very similar to conventional demographic noise in the predator-prey systems. This is due to stochastic effects of birth and death rates. However, here it's just like to simulate the vertical oscillations. And it scales with square root of B, which is the velocity roughly, and multiplied by power phi. And similar to what we have seen with numerical simulations for intermediate values of C and phi, which is noise and structural disorder, we have intermittent dynamics for the R, which is fractional mechanical energy, and we have totally turbulent case for larger values. And this is very similar to what we have seen in molecular dynamic simulations. Also, a single dimensionless number can be recovered from these equations, and it's equal to inertial term parametrized with disorder divided by gamma squared, which is damping. And for roughly intermediate values of theta between 10 and 100, the dynamics is the most intermittent. And which is very similar to Reynolds number for a pipe flow, where intermittent turbulence occurs between 1700 and 2300 for Reynolds number. So to sum it up, we have found this novel non-equilibrium phenomenon that describes intermittent turbulence in dusty plasma crystal. And we use simulations where we have determined the coupling nature between external driving and structural heterogeneities, and minimal model where vertical and horizontal kinetic energies are modeled as ecological species, and they undergo these oscillations due to spatial heterogeneities and noisy driving. The big takeaway from my talk is that our simple system can serve as a model for intermittent dynamics in many body systems. Thank you, and I would like to answer any questions if possible. Thank you once again.